Assalamu alaikum. Bismillahirrahmanirrahim. Let's start lecture number 6. In lecture number 5, we have studied zeroth law of thermodynamics, first law of thermodynamics, energy balance equation, that is delta E is equal to heat transfer minus work Q minus W, and solve basic numerical of closed system, in which we are solving the same energy balance equation. But for complex process or for later numericals, we have to study thermodynamic process. You already studied in your in inter these processes in Carnot cycle and reverse Carnot cycle. In later slide we will also study this process again, but here we will interested in isothermal process because we are going to solve the numericals of isothermal process. So we will study this isothermal process in detail, isothermal and adiabatic process. Isobaric and isochoric process is very simple. So before studying that process, we have to define the system by the state variable, and state variable depends upon condition of the system. These are the state variable parameter used to express state of the system. For example, for a compression process, in the state 1 the pressure is lower, volume is higher, and from when it going from state 1 to 2, the pressure increase and the volume decrease. So we are defining the state of the system by these state variable, and these state variable depends upon ideal gas equation, that is PV is equal to nRT, pressure, volume, number of moles, gas constant and temperature. I will not going to drive this equation because you already studied in pre-engineering. So let's move on towards the basic processes. For an example, like I've told the compression process, in figure you can easily understand that in figure 1 the volume is higher, pressures have some value and temperature have some value. But from this, if the process is going from state 1 to 2, the volume decrease. So on the expense of decreasing volume, the pressure will definitely rise if it is a isothermal process, and temperature is constant. Okay, now we by these state variable we are going to study isobaric process, isochoric process and adiabatic process. So from this diagram you can easily understand isobaric process. In isobaric process, this is state 1, this is state 2. In the isobaric process, let's suppose we have a volume 0.1 and 0.2. So from state 1 to 2, the pressure is constant, like we have 2 bar. So you can understand that in isobaric process, volume will increase or decrease, whether it going from this end or this end, but the pressure kept constant. So on the expense of this, the temperature will rise or decrease. When it has a compression process, when it going from 0.2 to 0.1 meter cube volume, the temperature will rise and the pressure has constant, and in that process the also heat transfer take place. Similarly, in isochoric process we have constant volume. For an example, we have volume 0.1 meter cube here. So from state 1 to state 2, the volume is kept constant, but pressure is rising from, let's suppose here we have 1 bar pressure, from 1 bar to 2 bar. So in this process we have constant volume but increasing pressure, so it's a isochoric process. Let's discuss isothermal process and adiabatic process in detail, because it is has similar pattern but two different paths. Why they are performing two different paths, we will discuss in later slides. We already discussed this. Isothermal process, in isothermal process temperature is constant. Isobaric process pressure is constant. Isochoric process volume is constant. In adiabatic process we have a constant heat transfer, and if it is an isentropic process, it will be a reversible adiabatic process. So first study isothermal process. In isothermal process, it is a process in which temperature remains constant throughout the process, not in state 1 or state 2, like in the figure number 2. In the figure number 1 you can see that from state 1 to state 2 the temperature kept constant. If we take this at a volume, so volume is increased but the temperature is constant, so it's an isothermal process. But in figure 2 the temperature values is same, like here we have, let's suppose, temperature of 4 degrees centigrade, and here we also have 4 degrees centigrade, but during the process the temperature is decreasing and then increasing, so it is not a isothermal process. It could be adiabatic process. Okay, now come towards adiabatic process. In adiabatic process, these are the two path of the two processes. This is isothermal process. In isothermal process, we are, as per Boyle's law, PV is equal to C, and when we write PVN is equal to C, is a polytropic process. It is a general process and the process is defined by the N. It is not a number of moles, it is a polytropic index which define the system. If N value has 1, then PV is equal to C, and we can call it isothermal process, and it will follow this path. But when the N value is 1.4, that is also called gamma, so then we have adiabatic process. In N, when we have a value of N is equal to 1.4, the heat transfer will not take place and the system will follow this path. What are the difference between two process? In adiabatic process, the V power gamma, that is 1.4, and 1.4 replaced with we have a symbol for the adiabatic process is gamma. V gamma is greater than V. Okay, when we solve these values, you can also experience in the numerical the V gamma value will be greater than value of volume, because gamma is greater than 1, that is 1.4. so pressure is inversely proportional to volume. So when the volume is increase as compared to isothermal process, pressure will decrease. So you can see the difference between the two same point. In adiabatic process we have a lower pressure, and in isothermal process we have a higher pressure. In both the system, in both the process, the difference is that in isothermal the temperature is kept constant during the whole process, but in adiabatic process the temperature will decrease and increase, but heat transfer becomes constant. So these are the some features or some relation that explain these processes. In isothermal process, temperature constant and defined by the equation PV is equal to C, and we can derive this Boyle's law, volume inversely proportional to pressure. When we remove this proportional sign, V is equal to C upon P, and then P comes over here, so the equation becomes PV is equal to constant. In this system, the total energy remains 0, and the total heat transfer is equal to the total work done in isothermal process, because when the temperature is not increasing, so internal energy of the system will remains constant or 0. It will not increase or decrease. Let's suppose you have already solved this numerical u2 minus u1. So we have same value in u2 and same value u1. So when we minus both values, the answer becomes 0. Now you can you already solved the numerical, so you easily understand this isothermal process. Isobaric process. In isobaric process, pressure is constant, and we have V, volume is directly proportional to volume is directly proportional to temperature, and when the proportionality remove, we have to put some constant Ct, and then constant is equal to V upon T. Okay, then in isochoric process, the volume is constant, P upon T is constant. So we have relation P is directly proportional to temperature. When we remove the proportion sign, we have to place a constant, and then P upon T is equal to C. You can see the equation over here. In adiabatic process, in this system, the Q in isobaric process, the delta Q is equal to delta U plus delta work done, because in this system the temperature is increasing or decreasing, whether is a increasing volume process or decreasing volume process, the temperature of the system will rise or decrease, so internal energy will change. So delta Q is over here, and in the same way the internal energy heat transfer will take place in the system. In the similar way, during the heat transfer, the internal energy will change, and during this process some work done the work done could be on the system or could be from the system. In isochoric process, work done is 0, because there is no change in the volume. So when the volume is not changing, so how can you convert energy into the work when we are not displacing piston? So how can we convert this changing volume work into work? So the work value will be 0. Also W is equal to PD. We already have in later slide we will also study this equation, that W is equal to P del V. So when the change in the volume is 0, so work is also 0 for the isochoric process, and the net heat transfer is directly is equal to the total change of internal energy. So when the work is 0, Q is equal to delta U. So when we are heating the system, it will increase the internal energy, or when the heat released from the system, the internal energy will be decreasing. So it is isochoric. In adiabatic process, the net heat transfer is 0. So the internal energy converts into the work. The internal energy of the gas moves the piston from point 1 to point 2. For an example, here we have a volume like 0.1 meter square, but the heat transfer is 0. For an example, we have an isolated system, so there will be no heat transfer from system towards the surrounding. So in that case, the internal energy of gas push the piston to point 2 meter cube. So in that case, the internal energy converts into the work. That's why we have placed the Q is equal to 0. So that definitely when the W is going over here, we have a negative sign. So from these relations and from these feature, I hope you will understand these processes. We will discuss this process in detail in later slides when we are discussing the Carnot cycle and reverse Carnot cycle. Anyway, now move towards the moving boundary work. One form of mechanical work frequently encountered in practice is associated with the expansion or compression of the gas in piston cylinder device. So it is a common application. We in our daily life we have a common application of compressor. When you go to any tire shop, you can see this kind of compressor which inflate your tire with the air. So it is a compression process. It is taking air from like in this figure you can see that the air is coming from here, then it hold. When the piston move here, it compress, and then the valve is open, and then air is releasing in that way. So it is a compression process. Similarly opposite to this, we can have a expansion process in which the air comes in, the piston move here, so the volume is increasing. So the increasing volume will decrease the pressure, so it's an expansion process. So in daily life we encounter these application. During this process, part of the boundary, the inner face of the piston moves back and forth. This expansion and compression often called boundary work. So in previous numerical, we have done the numerical with the fixed boundary. We have a fixed boundary, it will not changing. Sorry, why it is not going backward, I think. Yes, in this numerical the boundary is fixed, the boundary is not changing. We are adding work and the heat is released from the system, but boundary is not changing. But now we will solve the numerical in which the boundary of the system will change when it compresses the gas. The boundary of system is like this, and the piston come over here. So it's a changing boundary. When we have an expansion process, we have a boundary like this, piston is come over here, we have increased boundary. Similarly to this diagram. Yes. So to study changing variable boundary work, we have to understand the equation which define the work done by the system. For an example, consider the gas enclosed in the piston cylinder device shown in the figure. The initial pressure of the gas is P, the total volume is V, and the cross-sectional area of the piston is A. So cross-sectional area of the system is like when you see from this end, from the bottom end, the piston looks like this. So this is area, pi r square, and it is a circular cylinder. So this is area, this is the piston area. So when the area is constant, when we move piston either from this point to this point, the volume is increased by ds. Area becomes constant, and just by multiplying this change in distance, we get the increased volume. Okay, and we have initial pressure P and volume V. The total boundary work done during the entire process as the piston moves is obtained by adding all the differential work from initial state to final state. So we have to apply differential equation over here, because we have to understand the behavior of the process also, not just countering volume 1 and volume 2, and we know that work is pressure multiplied by change in volume. By doing this we get wrong answer. In the later slide we will see how. For an example, you can see in the particular this example, we have process A, in which in process A the path is going from state 1 to 2. It is a expansion process, and doing this it is following this path, and by following this path we have a volume 3 meter cube. Here a change in the volume is 3 meter cube, but the work done is 8 kilojoules. You can see that it covers lesser area. Okay, but similarly when the state is going from process 1 to 2, from state 1 to 2 during by process B, it will cover larger area. So in that case it will do more work, like 12 kilojoules. So we cannot it is not constant, not as constant like straight line. So we cannot apply the equation W is equal to P del V. We have to define by the derivation equation, derivative of delta S or delta W or delta V. If we multiply by ds into this area, it becomes dV. So general equation for solving this boundary moving boundary work is W is equal to integral state 1 to 2 P dV. So we have to solve this equation to find out work. I hope you get the answer of path function, why we are using this integral equation, and it will give accurate answer. You can use for initial purpose in pre-engineering. You studied that equation P is equal to W is equal to P delta V. It give answer, but it will not give accurate answer as shown in this particular diagram. So we already discussed that we have a general equation for the compression of expansion, PV N is equal to C. It is called polytropic process, and why it is called? It is a general process. The value of N can be 0, 1 or 1.4 or in between this between 1 to 1.4. So it changing the path of the system, as you see in the isothermal and adiabatic process. When we have a value of N is equal to 1, so it is a isothermal process. When we have a value of 1.4, we have a adiabatic process. And when, let's suppose, we have a value of N is equal to 0, then what happens? V power 0 becomes 1, so P is equal to C. Pressure becomes constant. So when the pressure becomes constant, it becomes isobaric process. And when the N becomes infinity, it becomes isochoric process. So polytropic is a general equation for compression and expansion process. And by defining that polytropic index, we can say what kind of process path will be, whether it is a isobaric path, whether it is a isochoric, whether it is a isothermal or adiabatic. In this figure you can see that use actual data from the experiment shown here to find a polytropic exponent for expanding air. see end of the chapter 4.174. So you can also refer the book Sengel. I have taken this diagram from the Sengel. We have a experimental machine which can calculate this value of n experimentally, that how the system will follow the path, either like this, either like this, either like this. So we have actual a practical machine which is calculating the polytropic index or polytropic exponent. Here here they show the difference between two. For an example, when we have a value of PV is equal to C, when the V comes from goes from this point to this, is become V minus N, and later we solve these numericals. So I hope you well understand by these process and how it is changing, what are the polytropic process, and by changing the index of polytropic, how the process path will be changed. And in the real practical life, experimental machine calculate the polytropic index or polytropic exponent. Both word can be used in thermodynamics. Now we are going to solve the numericals of moving boundary work, that is example 4.3 from the book Sengel. A piston cylinder device initially contains 0.4 meter cube of air at 100 kilopascal and 80 degrees centigrade. The air is now compressed to 0.1 meter cube in such a way that temperature inside the cylinder remains constant. Determine the work done during the process. So here we have to what happened? So here we have to calculate the work done. The same equation, P is equal to integral 1 to 2 P dV. But in this example, they are not telling the polytropic index, whether it is 0. It can be 0 because it is a by looking this picture you can see that it cannot be 0. N could be 1, and if it is a 1, it is a isothermal process. If it is a n.1.2, it is a polytropic process. If it is a 1.4, then it is a adiabatic process, and the value could be between 1 to 1.4, so on. So when they didn't tell the polytropic index, we can assume the numerical with the n is equal to 1, and we use equation PV is equal to C. So remember that even in the paper, when in the numerical not define the equation or polytropic index, we take n is equal to 1. So let's solve this numerical. And note, make new note. Yes. So first of all, we just write the data. We have initial volume V1 is 0.4, final volume V2 is 0.2, and P1 is equal to 100 kilopascal. So V1 is 0.4 meter cube, V2 is equal to 0.1 meter cube, and P1 is equal to 100 kilo Pascal. And they also tell us temperature, but we didn't require temperature for this numerical, because we have to solve the numerical from with this equation, and then W is equal to P delta integral P dV. So they also tell us the temperature, but in this particular numerical we didn't require this temperature. And as you can see that it is a compression process. The volume is decreasing 0.4 to 0.1. So let's solve the numerical. First, it is defined by PV is equal to C. It is a isothermal process. Then we place this equation in work formula, that is integral P dV. So it is a derivative of we have a derivation of derivative V, so we have to place P in terms of volume. So we make this equation like this: P is equal to C upon V. Now putting these into here, we have from process 1 to from state 1 to 2, we have C over V dV. Now we can moving towards next page. Now work, C is a constant, so it comes out, and the remaining is from state point 1 to 2 is dV. So what is the form? You already done this integration in second year pre-engineering. You can get this answer. Anything have a variable of denominator power 1, it can be used as ln V from state 2 1 to 2. So you can write. So the formula for integration of 1 over V is ln V, and then we open the limits. So we have limits, upper limit minus lower limit. Now by this subtraction formula, by the log formula, we can write this like V2 upon V1, and from C we can open the value of the C. C is equal to simple PV, and it could be I can write here P1 V1 is equal to C, or P2 V2 is equal to C. So in both state, C is constant and pressure volume values is differing. So in this particular numerical we have we have the value of V1. So we use this equation P1 V1 is equal to C, and displace C with P1 and V1. Now we are displacing C with P1 V1 and ln V2 upon V1. Now putting this value, how much the pressure is, P1 is 100 kilopascal, volume V1 is 0.4, and ln V2 is 0.1 divided by V1 is 0.4. Now solving this, we get answer 100 okay, by solving this equation, the unit of work will be joules, but we are not opening this kilopascal, kilo. So the answer will comes in the form of kilojoules. If we open this kilo 10 की power 3, तो answer is comes in the pascal. So we left this kilo format and get the answer in the kilojoules. So 100 multiplied by 0.4 multiplied by the ln 0.1 upon 0.4 is the get we get the value of 1.38 minus 1.38. Clearly write 1.38. Now we left pressure in the form of kilo, so we get answer in kilojoules. So we get the answer minus 55 kilojoules. If the pressure it is in the pascal format, then we get the answer in joules, but the pressure in the kilopascal, so that's why we get answer in kilojoules. So we solve this numerical. It's a very simple numerical. We first place W is equal to PdV and replace P with C over V, then solve 1 over V. Integration of 1 over V is ln V. Apply limits, put the formula for C is P1 V1, then putting all the values P1 V1 V2 upon V1, and we get the answer of work done, that is minus 55 kilojoules. Now you can notice that in this answer the value is we get the value having minus sign. What is it, what the minus sign indicates? The sign of convention that we have studied in lecture number 5, that any work in this process, it is a compression process. So work done is on the system, and when the work done on the system, we get the sign negative.